Imagine we have a set of data points. Our goal is to find a line that best represents the relationship between them. This is the fundamental idea behind linear regression. But here's an important question. What happens when the data contains an unusual point, also known as an outlier? Can a single point completely change our model? Let's find out. Before training begins, we need a way to measure how good or bad our predictions are. Linear regression uses a loss function called mean squared error, or MSE. Each blue point represents a real observation from our data set. The objective is to find a line that minimizes the overall prediction error. At the beginning, the model has no knowledge of the data. The line starts with initial values for its weight and bias. During each training iteration, the model makes predictions. It then calculates the error and adjusts the weight and bias using gradient descent. Notice how the yellow line gradually moves toward the data points. The dashed vertical lines represent residuals. A residual is the difference between the actual value and the model's prediction. As training progresses, these residuals become smaller. At the same time, the loss continues to decrease. This tells us that the model is learning a better representation of the data. After several iterations, the regression line closely follows the trend of the data set. But what happens if we introduce an outlier? Let's see that next. Our model now fits the data quite well. The residuals are small, and the loss has decreased significantly. Let's retrain the model after adding this single point. Watch carefully what happens to the regression line. Notice that the line starts moving upward. The model is trying to reduce the error caused by the outlier. Because mean squared error squares large mistakes, this point has a strong influence on training. Look at the weight value. It keeps increasing as the model attempts to fit the outlier. The result is a line that no longer represents the majority of the data as effectively. Is there a way to keep learning from the data while preventing large weights? This is exactly the problem that ridge regression was designed to solve. In the previous scene, we saw that a single outlier caused the model's weight to increase significantly. Large weights can make a model unstable and more likely to overfit the data. Ridge regression introduces a simple but powerful idea. What if large weights were not free? What if the model had to pay an additional cost whenever the weight became too large? Notice how the penalty changes. When the weight is 1, the penalty is only 1. When the weight increases to 3, the penalty becomes 9. And when the weight reaches 5, the penalty jumps all the way to 25. Large weights quickly become expensive. Linear regression minimizes only the prediction error. Ridge regression keeps the same error term, but adds an extra penalty term. This additional term discourages excessively large weights. The parameter lambda controls the strength of the penalty. When lambda is 0, ridge behaves exactly like linear regression. As lambda increases, large weights become increasingly expensive. Now that we understand the idea behind ridge regression, let's train it on the same dataset and see how it behaves compared to linear regression. Ridge regression uses the same prediction error as linear regression. But now we also add a penalty whenever the weight becomes too large. The model starts with 0 weight and 0 bias. During training, it tries to reduce prediction error while simultaneously keeping the weight small. Notice how the regression line still learns the overall trend of the data. However, it is no longer chasing the outlier as aggressively. The regularization term discourages excessively large weights. As a result, the model becomes more stable. The loss now consists of 2 parts: prediction error and weight penalty. Ridge regression tries to balance both objectives. We have now trained both linear regression and ridge regression on exactly the same data set. Both models saw the same outlier. Notice the difference in the fitted lines. Linear regression is pulled more strongly toward the outlier. Ridge regression remains closer to the overall trend of the data. Let's compare the learned weights. The linear regression model ends up with a larger weight. Ridge regression keeps the weight under control because large weights are penalized during training. This makes ridge regression more stable. Instead of focusing too much on a single unusual observation, it balances prediction accuracy with model simplicity. Ridge regression generally produces lower variance. It is more robust to outliers and noisy observations, and it prevents weights from becoming unnecessarily large. Ridge regression doesn't ignore the data. It simply adds a mechanism that discourages overly complex models. This often leads to better generalization on unseen data. Let's quickly summarize what we learned. Linear regression tries to fit the data by minimizing prediction error. However, when an outlier appears, the model may increase its weight significantly. Large weights can lead to overfitting and poor generalization. Ridge regression solves this by introducing a penalty on large weights. As a result, the model becomes more stable and generalizes better to unseen data. The key idea behind ridge regression is simple. It combines prediction accuracy with a penalty for large weights. This extra term acts like a control mechanism that prevents the model from becoming unnecessarily complex. The goal of machine learning is not just to fit the training data. The real goal is to perform well on data the model has never seen before. Ridge regression helps achieve that balance by combining accuracy with simplicity. Thanks for watching. Subscribe for more machine learning visualizations.